Welcome to Unit 8, Inference for Categorical Data, Chi-Squared. All right, this is topic 8.1. Are my results unexpected? And that's really kind of the big theme of this entire unit, is looking at results of samples and trying to figure out are they what we expected or are they something different? We're trying to find out, is there evidence that it's something different than what we expected? And this topic 8.1 is really just an intro to get you guys ready for what is known as Chi-Squared. So first off, the name of this unit is Inference for Categorical Data. So let's make sure we quickly remember what that is. As we've learned before, categorical data is collected from a categorical variable, which is a variable in which an individual can take on one of a limited and usually fixed number of possible values. Each individual is assigned to a particular group or category on the basis of some qualitative property, which is typically in the form of a word. So one easy one that comes to mind is eye color. I have blue eyes, so I am going to be assigned to that category of having blue eyes. And again, color, blue eyes, brown eyes, green eyes, those are words, and that's oftentimes the case for categorical data. So we have seen that with categorical data, you could calculate a statistic called a proportion. For example, you could look at the entire population and say, wow, 20% of people have blue eyes. Or you could look at just a sample of, 1,000 people and say, oh, only 14% have blue eyes. But the point is, when you take the number of people that have blue eyes, you count all of the people that said I have blue that fit into that category, and you divide by the total, that's called a proportion. So in Unit 6, we explored inference for a single population proportion and inference for the difference between two population proportions. But what if we want to examine the distribution of a single categorical variable in a population? So what exactly do I mean by this? Well, back in Unit 1, we might have said, or back in Unit 6, excuse me, we might have said, somebody told me that 20% of people have blue eyes, and I want to find evidence that it's actually less than 20%. I was only looking at one population proportion, the proportion of people that have blue eyes. And then we also looking at the difference between two populations. So we might say, hey, is the proportion of people that have blue eyes different than men and women? So is there a difference between the proportion of people that have blue eyes amongst men and women? Or maybe a whole other example could be something like, what proportion of people own a Ford car in the US versus China? But the point is, we're only looking at one category within that variable. So you think of eye color, we were only focusing on blue. Or the category of what kind of car do you have? Well, we were only focusing on Ford. But what if we want to look at the entire categorical variable? Eye color, not just blue, all different eye colors. There's more than just one. Or all manufacturers of cars. You got Honda, Chevy, Hyundai, Kia, Ford. You got a ton, right? We don't want to just concentrate on Ford. We want to look at the entire categorical variable of car manufacturers. And that is going to require a chi-squared test. So that's the difference between this unit and the unit we've done before, is that we're not just focusing on a single category within that categorical variable. We're focusing on the entire categorical variable itself. All right, so there's actually three different types of chi-squared tests. So it's actually really good because we're going to look at these examples for the rest of this unit. So it's a good idea to kind of get a feel for what I'm talking about here. So this is known as a chi-squared test for goodness of fit. This allows us to determine whether a hypothesized distribution seems valid. Now, again, there's a lot to go into this unit, so let's just kind of take it slow here. So here's an example. Sample 450 people showed the following breakdown of eye color. So this is clearly categorical: blue eyes, brown eyes, green, hazel, amber. Those are the 5 major eye colors that are out there. So we see this distribution, but we also read, maybe on the internet or something, or in some kind of magazine, that the distribution across the entire population of the human race follows this, right? 10% blue, 78% brown, 2% green, 5% hazel, 5% amber. So the question is this distribution valid, right? Obviously, don't expect that we're going to see the exact same proportions in a sample, because definitely we have learned one thing this year, and that's that samples vary. So the question is, are these percentages that we thought were valid, are they still true, or is there evidence that it's something different, that the numbers are just too far off, that maybe these values that we thought were true for the breakdown of eye color are no longer true? So that's going to require a chi-squared test. Again, because we're not just focusing on blue eyes. If we were only focusing on having blue eyes, in this case it says 10%, that would go back to Unit 6. We're just looking at one proportion, but we're not. We're looking at the entire categorical variable of eye color. Here's another example. This is called a chi-squared test for homogeneity. And a chi-squared test for homogeneity can help us decide whether the distribution of a variable differs for two or more populations. So we're looking at a categorical variable, but across 2 or more populations. So again, we're not like, I mentioned earlier, we could look at blue eyes for guys versus girls. Well, that's looking at one category. I want to look at the entire categorical variable across different populations, not just focusing on one. So here's an example. We looked at data from 3 random samples of middle schoolers, high schoolers, and college students, and we looked at the social media preference. So we saw Facebook among some of them, Instagram among some of them, and Twitter among some of them in terms of what they perform most. And the question is the distribution the same or different across those populations? So for example, if we look at this data of the middle schoolers, 12 out of 150, and that's 12 out of 150, excuse me, I should do the calculation real quick, it's 8%. Sorry, I should have known that. So 8% of middle schoolers use Facebook. Okay, well, if you look at college students, it's 44 out of 220. It's about 20%. So we got 8% of middle schoolers using Facebook and 20% of college kids using Facebook. Now, if that was all we were focusing on, just users of Facebook amongst middle schoolers and users of Facebook amongst college students, well, again, we can go back to Unit 6. But notice we have high schoolers. So we actually have 3 middle schoolers, high schoolers, and college. But we don't just have Facebook. We have Instagram and Twitter. So to answer this type of question, we really need what's the chi-squared test, this brand new test that we're going to learn about this unit. So the idea here is that we want to say, hey, we see, are the distributions the same? Like, let's just say 15% like Facebook, blah, blah, blah percent like Instagram, blah, blah, blah percent like Twitter. And is it the same for each population, middle school, high school, college? We know there's going to be subtle differences because that's what samples do, right? But are they so far apart, like 8% for Facebook, middle school, 20% for college? Is that so far apart that we could say that the distributions are different? And again, that's what we need a chi-squared test for, because we're not just looking at Facebook. We're looking at Facebook, Instagram, Twitter across 3 different populations. And here's the last type of chi-squared test that we're going to look at in this unit, and that's a chi-squared test for independence. A chi-squared test for independence allows us to see if there's convincing evidence of an association between 2 variables within a population. So for example, does the data taken from a random sample of people in a county, so let's say we looked at one county in Pennsylvania, and we want to say, all right, is there an association in that county amongst gender and political party preference? So we have males and females, we have some of them are Democrats, some of them are Republicans, some of them are independent. And the idea is we want to determine, is there an association, right? I'll go back to what I've kind of been doing a lot in this video is, if we were going back to Unit 6, we would say, all right, let's just compare Democrats Democrats amongst females versus Democrats amongst males. That is a 2-sample Z test for proportions, looking at the difference between 2 proportions. But again, we're not just looking at Democrats. We're looking at Democrats versus Republicans versus independent, and we're looking across these 2 genders to see if gender plays a role in what political party that you're affiliated with. And that is allowing us to see if there's an association. And that's going to require, again, the chi-squared test. Just because they're a little bit off might not mean a whole lot, but are they so far off that we could say, whoa, a lot more males are Republicans or a lot more females are Democrat? And again, we need a chi-squared test to make that decision. All right, so here's the big idea. The big idea that we see in these problems is that our data is never, I can't repeat that enough, it's never going to match up perfectly with what we were expected or what we was told to be true. We were told 10% of people have blue eyes. We might have saw 12%. All right, that's just part of sampling. It's never going to match up perfectly because we live in a world where everything varies. But we do need a significant test to determine whether the differences we are seeing are A, due to just that general variability that comes with random sampling, or are the differences so large that it's due to a fact that it's something outside of randomness, right? Due to the fact that our data doesn't fit with what was expected for a reason beyond randomness. So this is kind of like, the battle cry, right? When you see a group of data, you have to first understand you're never going to see exactly with what you expected. But your job as a statistics student is to determine, are we seeing small differences that are just due to variability? Or are we seeing such large differences that it's something more is going on here? Like maybe men really do favor a Republican, or maybe middle schoolers really do favor Twitter. And that's why we need to run these tests to determine if there's small differences that is just due to variability, or large differences that are for something that is, more important. So here's the basics. Just think of this as another significance test. We've been learning five. We've learned 5 different significance tests if you actually go back and count them all. So this is no different, right? There's going to be 4 steps. You're going to have hypotheses. You're going to have conditions. You're going to have work. You're going to have a conclusion. So none of that is really different. But here's kind of the good news is there's only one formula we're going to need for the entire unit. So, with proportions and means, there's multiple formulas for this and that and all the yada yada. Here we just have one single formula, and this is called the chi-squared formula. Now let's just talk a little bit about chi-squared real quick. The Greek letter chi is, it's an X essentially, but this part is a little curvy, this part is straight. So that's chi, and then we call it chi-squared. Some people just write that symbol right here and it's pronounced chi-squared. Some people just put chi-squared, right? They just spell it out, C-H-I squared, right? It doesn't matter. It's up to you. It's whatever you want to do. But the Greek letter chi is C-H-I, and it looks like a slanted, slightly curvy X, okay? So this is the formula for the chi-squared statistic. It's in a sense like a z-score or like a t-score, but obviously it's a very different formula. But we'll get used to using it, and like I said, the good news, it's literally the only formula. Now, there's also no confidence intervals this unit. Chi-squared doesn't have any confidence intervals. It's all about conducting a test. So the next few topics will explain what this formula represents. And also note it is given to you on the AP Stats formula sheet, so you don't have to worry about memorizing it. And chi-squared is known as a non-parametric test. It meant that we do not have to make any assumptions about the underlying parent population. So we don't have to worry about, is there a normal distribution going on here? Are we big enough to be normal? Do we have to check successes and failures? Or do we have to be bigger than 30? No, none of that is going on here. So that actually makes this a little bit easier. But at the end of the day, at the end of this entire unit, you are going to learn 3 different types of chi-squared tests that all really kind of follow the same format. It's a chi-squared test for goodness of fit, which some people just abbreviate GOF, goodness of fit, chi-squared test for homogeneity, and a chi-squared test for independence. Just know this real quick, and I explain this in later videos as well, but the chi-squared test for goodness of fit is if you only have one categorical variable, just one, get hair color, done, that's it. Eye color, done, that's it. Whereas homogeneity and independence deal with 2 categorical variables. So, age, high school, middle school, college, and which social media do you prefer. So there's 2 categorical variables going on. Gender, male, female, versus political party, Republican, Democrat, Independent. Again, 2 categorical variables going on there. So that's homogeneity and independence. But a chi-squared goodness of fit test, 1 categorical variable. So, of course, there are going to be hypotheses, and the good news here is hypotheses are written words. There's no numbers, no symbols for the hypotheses. We are going to have to calculate degrees of freedom here as well. A little bit different, but again, I'll explain it all in the upcoming videos. And, of course, there is going to be the step of checking our conditions. We have to, of course, make sure that the data was randomly selected to avoid bias. We still have to make sure that our samples are independent of each other. So we have to make sure that the sample size is under 10% of the population. Let me just briefly go over that one more time. Remember that when you draw samples from a population and you do not replace them, when you go ahead and take another sample, another sample, another sample, you are actually going to get different results because you are slowly changing the population by not replacing. And that's where the 10% condition comes in. It says, listen, you don't have to worry about any very subtle differences as long as your sample size is under 10% of the population. And again, like I just mentioned earlier, there is no condition we have to worry about the shape. So this is the third condition is actually that we need the expected values to all be 5 or more. And again, I know I'm going through a lot of that doesn't quite make a lot of sense right now, but it will once we start learning the individual tests in the next couple of videos. Again, this is really just kind of an intro to get you guys ready for what you're going to be learning. That way it all makes sense to you and you're ready to go. All right, guys, that's it. See you in the next video where we start to tackle goodness of fit.